Thank you, and thank you for the invitation to lecture at this school. So my first two lectures are going to be about some basic aspects of algebraic quantum field theory. And in the third lecture, I'll discuss more recent developments involving algebras of observables in quantum gravity. Actually, the first two lectures will be largely elaborating in more detail on things you've already heard introduced by Pablo Bueno in his two lectures. And I have there are two definite topics I want to address. If I have time, I will discuss some more things. I haven't exactly given these lectures before, so I'm not sure how long it will take to discuss my two topics. But the two topics I definitely want to explain are the Riesz-Leiter theorem, what it is and how to prove it, and why is relative entropy in quantum field theory well defined, even though ordinary entropy is not. So, on the first topic, the Riesz-Leiter theorem is important because it's the basic result about entanglement in quantum field theory. So, it's important to be familiar with it, and I think it's illuminating to understand something of why it's true. That's why I'm going to make the effort of proving it. I'm using this tablet instead of writing on the blackboard because I think you'll be able to read what I write better, although at least when I'm sitting down and writing it, you'll see me less. So let's first, just to set the stage, and here I'll be repeating kind of the beginning of Pablo's talks. We start with Minkowski space, with time running up, and then we consider a region in space-time, like this region, which I'll call U. And now we can ask, what can we say about what's in U? Well, we can't say what particles are in U. That's actually not a good notion in relativistic field theory. In non-relativistic quantum mechanics, there's an operator that would tell you if a particle is in a given region of space. But that doesn't work very well relativistically. So we don't want to say what particles are in U, or what Hilbert space state is in U, but we can discuss operators in U. Operators can be better localized than particles because in quantum field theory, first of all, we start with local operators 5x. As I'll discuss in a little bit more detail later on, 5x isn't quite well defined as an operator. To really make an operator, we should smear it and consider something like phi sub f, where f is a function with support in U. So f is supported in U, which I'll just loosely write this way. That just means f is 0 outside of U. So strictly speaking, this kind of thing is a better defined operator, but more informally, when it makes sense, we can just use local operators. At any rate, since a local operator can be defined by a point, and smearing can be carried out in a small open set, operators in an open set are well defined, even though we can't say precisely what particles are in an open set. So we make an algebra that I'll call AU, which is the algebra of all operators in the region U. And we'll be discussing some properties of this algebra. Well, we'll be discussing in much more detail a small fraction of the things of which you heard an overview in Bueno's talks. Now, one basic fact is that if we have a region U of space-time, there will be another region, space-like, separated from it. So, in the case I'm drawing, V exists on both sides of U if we're just in 2 dimensions. Remember, time is running vertically in the picture. In more than 2 dimensions, V would exist everywhere around U, but regardless, there is this region V which is space-like separated. Then we'd have the 2 algebras, AU and AV, and their properties that they commute with each other. And as Bueno mentioned, in what are called Hogg dual theories, which roughly speaking are complete theories, in a sense you'll hear about, I think, from Cassini, they're maximal under the condition of commuting with each other. So in such theories, AV consists of everything that commutes with AU. That won't be so crucial in my lectures, though. Now, in quantum field theory, by definition, the Hilbert space or in general the vacuum sector if there are superselection sectors. But we are not going to worry about superselection sectors, so we'll just say the Hilbert space is spanned by states obtained by acting on the vacuum with local operators. So states obtained by acting on the vacuum state with the product of local operators span the Hilbert space. That means that you could make a basis of Hilbert space states consisting of linear combinations of such states as I've written. So it follows that if any state chi in Hilbert space, an equivalent statement is that if any state chi in Hilbert space has the property for all points x1 up to xs and all s, those conditions imply that chi is 0. Well, why is that? Well, if there was a non-zero chi that satisfied this, that would tell us that all these states live in the orthocomplement of chi, which would be a proper subspace of Hilbert space. So when we say that these states span Hilbert space, that's equivalent to saying that they're not contained in any proper subspace, and therefore any chi that satisfies this condition must vanish. Now, the Riesz-Schlieder theorem says the remarkable property, which at first sounds impossible. This is still true if we restrict to the case that all the points x1 up to xs are contained in some possibly very small open set U. So even if we only act on the vacuum with operators in a small open set, we can still create all states in Hilbert space, including, as in the example Bueno gave, a state in which there is a peanut in Alpha Centauri, or to begin with, a state in which the galaxy Alpha Centauri exists. We could create it by acting on the vacuum with local operators in a small region in this room. So the proof is going to involve two facts. One fact is that the energy is non-negative in all Lorentz frames. So that's the basic fact about, I think that's the most important fact we'll use about relativistic field theory, that the energy is positive in all Lorentz frames. Of course, we'll use translation invariance. That's implicit. First you have translation invariance, then the corresponding conserved charges or the energy momentum, and then the assertion is that the energy momentum is such that the energy is positive in every Lorentz frame. We're also going to use the following fact, that if we have 2 points in space and time, you can get from one to the other by going first forwards in time in one Lorentz frame and then backwards in time in another Lorentz frame. Of course, if the 2 points are time-like separated, you can do it in one step, either forwards in time or possibly backwards in time, depending on whether the points are future separated or past separated. But if the points are space-like, of course, that means that you can't get there by a one-step time-like jump, but you still can get from x to y by going forward in time in one time-like direction, and then backwards in time in a different time-like direction. Which two time-like directions you have to use will depend on which spatial direction x and y are separated in. And when we make this argument, we're going to use the fact that the energy is positive in the frame in which this direction is the time direction, and it's also positive in the frame in which this direction is the time direction. But since we'll have to, in general, use all possible time directions depending on what time-like directions, depending on x and y, we really will use the fact that the energy is positive in every Lorentz frame. So, in making the proof, we know that, as I told you, if a sum state chi is orthogonal to 5x1 up to 5xs acting on the vacuum for all x1 to xs, then chi is 0. But we want to prove, still true, if we only know this, if the points are in some possibly very small open set U. U is our open set that we started the discussion with. So I'm going to prove this stepwise. I'm going to first show that if it's true when all the points are in U, then it's also true if all the points except the last one are in U, and the last one can be anything. So I'm going to first remove the constraint on x of s. And I'm going to do this by first showing that nothing bad happens if we move xs forwards in time in one Lorentz frame, and then that nothing happens if we move it backwards in time in a different Lorentz frame. But since that forward-backwards motion can move xs anywhere, that will remove the condition on xs entirely. So how do we first show that nothing goes wrong if we move xs forward in time? We pick a time-like vector u. U is a time-like forward vector. So in some Lorentz frame, it would just be 1, 0, 0, 0. But in general, u is any time-like vector. And we're going to look at the same function, but with xs replaced by... actually, I'm going to call the time-like vector t. It's more suggestive of time. And then I'll let u just be a real number. So I'll replace xs by xs plus a real number times t, where t is a fixed time-like vector. Then I let this act on the vacuum, and I do nothing to the other guys. And I regard this as a function of u. And we know that this function is 0 if the point xs plus u times t is contained in the set capital U. Is in the set U. And that's true for small enough little u, because our point xs is somewhere in the open set, and if you move it a sufficiently small amount, it's still in the same open set. So one thing we know to begin with is that this function f of u is 0 for sufficiently small u, positive or negative. Now, another way we can describe the function f of u is by introducing the Hamiltonian in this Lorentz frame. So I write e to the iuh phi of xs times e to the minus iuh. So H is the operator that translates xs in the t vector direction. So therefore, e to the iuh conjugation by e to the iuh replaces xs by xs plus ut. So this being equivalent to this is pretty much the definition of what the Hamiltonian does. But the Hamiltonian annihilates the vacuum. So I can erase this guy. And the operator e to the iuh is unitary if u is real. But because the Hamiltonian is bounded below by 0, the value for the vacuum, if we give u a positive imaginary part, e to the iuh makes things smaller. So f of u is holomorphic in the half plane mu positive because h is equal to or greater than 0. That might be more obvious if I write f of u in terms of a sum over intermediate states. I'll insert a sum over intermediate states. And then e to the iu will become e to the iu en, where en is the energy of the nth state. And the ENs are all non-negative and strictly positive except for the vacuum. So since En is positive, if I give you an positive imaginary part, that damps out the states with large energies. So when U has a positive imaginary part, this sum is rapidly convergent. And so the function is holomorphic in the upper half plane. So now we have a function that has two properties. F of u is holomorphic if the imaginary part of u is positive, and f of u is 0 if u is real and small. Well, the two properties imply that f of u is identically 0. You see, we know that f of u is holomorphic in the upper half plane. If it was, there's a region of the real axis where f is 0. Let's say this is the axis of real u, and f is 0 in this interval. And then we have holomorphy above the axis. If we had holomorphy on the axis in the interval where f is 0, hopefully you'd all immediately know that f would be 0, because a holomorphic function that vanishes in an interval would be identically 0. Its Taylor series expansion has to be identically 0, and then it is identically 0. We need to prove something because we only have that f is holomorphic above the axis. But you see, we can write a Cauchy integral formula. So u is holomorphic. I drew a little contour, which is a semicircle above the axis, and it has an interval on the axis. I'll call that contour gamma. And you see, f of u above the axis is the integral over gamma du prime over u prime minus u, f of u prime, I guess over 2 pi I. That's a contour integral formula. That's just a Cauchy integral formula. To be safe, you could have drawn the Cauchy integral formula starting with the contour that was slightly above the axis. And then you move it down to the axis. And then you move it down, by continuity, you can move it down to the axis. When you reach the real axis, you can throw away the part that's on the real axis. because f is 0 there. So now we have a Cauchy integral formula. Could I do what? Yeah, oh, thank you. So scroll down. Yes. Oh, sorry, this is meant to be minus 1. Yeah. I inserted a complete set of states to the left of the last operator, so there were only s minus 1 operators before it. And then because e to the I, u, e, n, well, most states have high energy, so this sum is rapidly convergent if u has a positive imaginary part because it exponentially damps the sum. Okay. Sorry, thanks for pointing out the error. So this should have an s minus 1 here. And what I'm trying to explain down here okay. To make this argument carefully, we'd start with this kind of contour. What we knew from the previous argument is that f is holomorphic in the upper half plane and continuous on the boundary, on the real axis. So we could start with a Cauchy integral formula like this, but then we could move it down to one that looks like this. It takes a little more practice than it looks to use this thing. Then you can move it down to the case that part of the contour is on the real axis. But then you can throw away that part of the contour because the function is 0 there. So at this stage, our integration contour in the Cauchy integral formula is just a partial contour like that. I'll call it gamma prime. So f of u is the integral over gamma prime f of u prime du prime over u prime minus u. And now it's obvious that we do have holomorphy on the real axis and even below the real axis, because in the Cauchy integral formula we're only integrating over gamma prime. U is somewhere here, but if we bring u down to the real axis or even through the axis, nothing happens. So we learned that f of u is actually holomorphic on the axis and below it. But once we know it's holomorphic on the real axis where it vanishes identically in a portion of the real axis, hopefully you know from your knowledge of complex variables that that means that f is identically 0. So we've learned that moving the point xs forwards in time or backwards in time, moving it in time in some given time-like direction didn't affect the vanishing of this matrix element. That was the main step, which we'll just repeat. So I'll stop here for any questions about it. Yes?
The fact that you use the time translation is because of the h is bounded below the user.
Yes?
Can't you do the same with the translations in spatial, but not try to use u in the whole upper half plane, but in another region? In a region where the function is holomorphic?
Well, the function will not be holomorphic. If you translate it in a spatial direction, you will not have any holomorphy in either the upper or lower half plane because the momentum is unbounded both above and below. The energy being bounded below gave us holomorphy in the upper half plane. If it had been bounded above, we would have gotten holomorphy in the lower half plane. If we have no bound above or below on the momentum, we would not get holomorphy above or below. Any other question? Yes?
You say that you mean that the spectrum of the Hamiltonian had to be positive?
Yes.
Another condition to ensure the holomorphic of the function, or only with that is sufficient?
Well, we need to know that, roughly, we need to know that the energies go to infinity. If there were infinitely many zero energy states, the energy would have been bounded below, but it wouldn't have been good enough for this argument. The argument I've given you is essentially the basic holomorphy of correlation functions. You can read about it in more detail, I guess, in Streeter and Whiteman, for example. Any other questions? So we learned, what we've done so far, starting with the fact, well, so we've learned that for any u, as long as x1 up to xs are in the small region, this function vanishes. But that isn't true, of course, for arbitrary xs. That's only, if you think about it, we started with xs in the region u, and we moved xs in a time-like direction. So at this point, x sub s has been replaced by any point that's time-like separated from the region u. But not all points are time-like separated. We want to also cover what happens if x sub s is moved to be space-like separated. So now we're going to look at this function, g of u prime. Well, we pick another time-like vector, t prime. But now we add u prime times t prime to the argument of the last operator on the right. And now we want to prove that the function g is identically 0. Well, how do we do that? Well, the steps are the same as before. First, g is 0 if u prime is sufficiently small. Oh, g is originally defined for real u prime, so that we're translating the point while it remains in real Minkowski space. Then if u prime is sufficiently small, you can think of u prime t prime as in addition to xs. It kept xs in the small open set we started with. And then, as we learned before, varying u didn't matter. So for u prime sufficiently small, well, another way to say it is that if u prime is sufficiently small, this point is time-like separated from the original region. So the previous argument applies. Then we learned that we're going to show that g is holomorphic if the imaginary part of u prime is positive. The argument is the same as before. We write g of u prime by inserting e to the I u prime times h prime. H prime is the Hamiltonian in some other Lorentz frame in which t prime is the vector in the time direction. This other Hamiltonian also annihilates the vacuum, and it's also bounded below, and its being bounded below leads to the same holomorphy we had before. And therefore, the same argument about analytic functions shows us that g is identically 0. So g is identically 0. So now we know that 0 is equal to our matrix element. If the first s minus 1 points are in this small set U, possibly very small set U, with no condition on xs. So we've removed the constraint on xs. Well, now we would like to remove the constraint on xs minus 1. How do we do that? Well, the same thing again. We look at the function h of u, let's say. Now what we're going to do is translate the last two operators in a time-like direction. We're going to make exactly the same argument as before. See, first of all, h is 0 for sufficiently small u, because for sufficiently small u, we have not moved xs minus 1 out of the open set it started in. And we know there's no condition on xs anyway. So h is 0 for small u. And then we can rewrite it with an insertion of e to the iu h. And then again, e to the minus iuh annihilates the vacuum. And the insertion of e to the iuh is heavily damped if u, for high energies, if u has a positive imaginary part. So h is holomorphic if the imaginary part of u is positive, and therefore h is 0. So now we know that our function vanishes if the first s minus 2 points are in the open set u, and the next one is time-like separated from u. And there's no constraint on the last one. But we want to worry about the possibility that this next to last point could be space-like separated from the original set u. Hopefully by now you can guess what we are going to do. We pick another time-like vector t double prime, and we define a function k of u double prime maybe. Where we now shift the last 2 points by ut plus u double prime t double prime. We can't use the same t prime as before because it might be we have to move in a different space-like direction. And so we pick some, in general, new t double prime. And we want to show that k is identically 0. We do that with the same 2 steps as before. It's 0 if u double prime is sufficiently small, because in that case the slightly shifted points obey the same conditions that we already just proved were sufficient. And it's holomorphic in the upper half plane because you can write it by inserting the Hamiltonian in a different Lorentz frame. I'm going to save a little writing now because you're probably getting tired of my saying the same thing over and over again. So the same 2 steps as before apply, and so we learn that once we learn that we could shift the last point in an arbitrary way, we learn that we can shift the last 2 points together in an arbitrary way. So by now, there's no condition on the last 2 points. Yes? What did you ask? Oh, you're right, sorry. Okay. So now there's a condition on the last 2 points. xs minus 1 and xs. Now, hopefully you might be inspired to guess how we generalize from that. Now that we know that there's no condition on the last 2 points, we translate the last 3 points together in a common time-like direction. We make the same argument using vanishing in a small set and holomorphy, and then we do it again with a different time-like direction. So we've removed the condition on the last 3 points. And then we do the same thing for the last 4 points. And finally, at the last step, we translate all s points together in various time-like directions. So in the end, we remove all constraints. On the points. And therefore we get the Riesz-Leiter theorem that if a state is orthogonal to all these all these states, if the points are in U, then chi is 0. Or equivalently, the usual statement, the states obtained by acting on the vacuum with field operators in U span the Hilbert space. That's the way Riesz-Leiter is usually stated. I hope it's obvious that it was only for notational convenience that I considered a theory with a single scalar operator phi. We could have been doing QCD with infinitely many local operators needed possibly to generate the operator algebra, and we would have made the same arguments. Any more questions about this?
I have one question.
Yes?
This is very surprising.
Yes.
Is there any intuition why it should happen?
Well, I'm going to explain what it means, actually elaborating on what you heard from Bueno, by discussing what would be analogous in ordinary quantum mechanics. But I will do that in a second. There's an important corollary. Let O be any operator in the algebra of the region U. So, for example, O could be a linear combination of things of the type we've been discussing. Okay. Sorry. I need to assume that U is small enough so that the spatial complement region V is non-empty. So this is meant to be the zero set, but it looks like the field operator phi. So I'll just say in words, V is non-empty in making this argument. So the corollary is that assuming the open set U is small enough that it's space-like separated from some other open set V, if O is any operator in that region, then O acting on the vacuum is not zero. Why is that true? Or maybe I'll say it a little bit better. If O is 0, then the operator U has to be 0. O has to be 0. If O is any non-zero operator in the open set U, it can't annihilate the vacuum. So how do we prove that? Well, suppose O annihilates the vacuum. And consider points x1 up to xs, which are in the region V. Then O acting, now look at the O acting on phi 1 up to phi xs on the vacuum, where we're given that x1 up to xs are now in the region V. Since they're in the region V, which is space-like separated from U, and O is in U, it follows that O commutes with the phi's. So this state is equal to phi of x1 up to xs acting on O on the vacuum. But if O annihilates the vacuum, then this is 0. So if O annihilates the vacuum, it has got to annihilate everything that can be created from the vacuum by operators acting in region V. But the Riesz-Leiter theorem told us that the states that can be created from the vacuum by operators in region V span the whole Hilbert space. So it would follow that O annihilates anything, and therefore O is 0. So the only the only state the only operator in a given region that annihilates the vacuum is 0. Any other operator has to create something non-zero. So there are two dual statements. The algebra, I've proved two things. The algebra AU has the property that it creates all states. That's described by saying that the vacuum state is cyclic. I find the terminology strange, but the usual terminology is that the vacuum state is cyclic for the algebra AU. And any operator, non-zero operator in AU does not annihilate the vacuum. That's described by saying that O is separating for AU. And a little thought will show you. You see, I showed that the way I showed you that omega was separating for AU was by using the fact that it was cyclic for AV. And as an exercise, you can run the argument in reverse. If you assume I proved actually just now that if it's cyclic for one algebra, then it's separating for the other. And the opposite is also true. If it's separating for one algebra, then it's cyclic for the first. Yes?
Is it important here that the operator O is bounding because it actually is null over a dense of the Hilbert?
I'm not sure I fully understand the question. I think it's not important. What is important is that the operator is in the region U. But I didn't give a careful mathematical definition of exactly what that means. We're being a little bit informal. But anything you could sensibly call an operator in the region U has this property that it can't annihilate the vacuum. Any other questions?
Sorry, did you define the algebra with capital A? Or small a?
I have. Well, this was meant to be a calligraphic capital A if we were using tech. I haven't intentionally written any small a's. But I'm not sure I understand the question, though, because This is meant to be O here. The corollaries.
Yes, up.
The corollary asserts that any operator in the region U that annihilates the vacuum is identically zero. Or to say it differently, any non-zero operator does not annihilate the vacuum. Did that answer your question?
No.
What was your question?
You define it with capital A.
The,
I don't know if it's the same algebra or not.
I've only talked about one algebra for the region U. I don't understand the question, I'm afraid. But the essence of the argument for the corollary was that an operator in the region U commutes with all the space-like separated operators in the region V. And since the operators in region V can create everything, as we've already proved, if O annihilates the vacuum, it has to annihilate everything, because it commutes with all those operators in region V. There was not meant to be any typographical delicacy in any of those statements.
No, sorry, it's just a matter of notation.
I think they refer.
When you write corollary,
The
there
corollary.
is a capital
Yes.
here.
Oh,
Sorry.
yes?
Can you elaborate a bit more? You mentioned that if you have a degenerate vacuum,
Yeah.
the argument doesn't.
Well, infinite. We don't have it in quantum field theory. We don't have a degenerate vacuum. The vacuum is unique.
Yeah.
Okay. In quantum field theory, energies grow fast enough to justify the argument I made. You see, so suppose that U is A plus IB, where A and B are real. Then e to the IUH is e to the IAH, which is unitary, and therefore won't affect anything we said, times e to the minus BH. And e to the minus BH is very highly convergent in quantum field theory. Basically, anything you ever run into in real life converges if you put in a factor of e to the minus BH. We could discuss precise statements, but I think it would be too much of a distraction. E to the minus BH propagates us in imaginary time by an imaginary time beta, B. And imaginary time propagation kills anything that smells like a divergence. So this is very strongly, very strongly convergent in quantum field theory, which means holomorphy. So holomorphy means you could differentiate it. Holomorphy means you can differentiate it. Well, so if you take e to the IUH, naively d by du bar of it is 0. But if that was going to be wrong, the way it would be wrong would be that the sum overstates that is implicit, or things don't converge. But it's actually extremely well convergent when U has a positive imaginary part. Yes?
So what we showed is that if you have an annihilation operator, it can't live in a local algebra, right? So
That's one thing we showed, yes. An annihilation operator annihilates the vacuum, but it can't have bounded support.
okay, so where does it live, that operator?
Well, you're the one who's picking the annihilation operator, but if you're writing it as integral over 3 space times some smearing function, the smearing function has support everywhere. It could have isolated zeros, but it can't vanish in an open set. If you have a smearing function that vanishes in an open set, the operator you've constructed is not an annihilation operator. The usual annihilation operators, people integrate them over all of space, right? So you're correctly saying that a special case of this is to ask in free field theory, could we find a linear combination of annihilation operators that is supported only in the region U? We've proved the answer is no.
I want to follow up with that. So, is there any restriction on this operator, right? Whether it have to be Hermitian or something like that?
No. The operator phi? You see, as I said, it was purely for notational convenience to write a single operator phi. We could have had a theory with many different operators. I could have been talking about phi 1 of x1 times phi 2 of x2, and so on, up to phi s of xs. All the steps would have been the same, except that this is supposed to be chi. I nowhere use the fact that I have the same operator everywhere. So asking about phi not being Hermitian adds nothing. A non-Hermitian operator is a Hermitian operator plus I times another Hermitian operator. And since in this argument we could have any number of operators, it's totally irrelevant whether the operator is considered a Hermitian or not. Any other questions? Yes?
So you showed that you can span the Hilbert out of operators in a region. So if I have an operator outside,
Yes.
and I insert it, this means that this operator outside should be written as a combination of the ones inside?
No, no. Okay, that's an excellent question, but the answer is no. What we proved is that it doesn't create any states that couldn't be created from inside. But it doesn't follow that the operator is a linear combination of the operators inside. Acting on the vacuum, it doesn't create anything. The operators localized in Alpha Centauri could have created a p-naught in Alpha Centauri. We ourselves as well, living here, could create a p-naught in Alpha Centauri if we're allowed to act with non-unitary operators on the vacuum. But acting on something other than the vacuum, the p-naught operator in Alpha Centauri creates something different from the p-naught operator here. All we proved is that acting on the vacuum, the operator there creates something we could have created. We didn't prove that the operator there is a linear combination of the operators here. That's completely false, and when I discuss now the analog of the Riesz-Leiter theorem in ordinary quantum mechanics, it'll hopefully be obvious that it's false.
But can we say that it is linear in a way, in the way topology?
No, no, not at all. So, in quantum field theory, we have two algebras, U and V. But in ordinary quantum mechanics, we can more simply have two systems. A and B, with Hilbert spaces HA and HB. So the combined system, which I'll call AB, has a Hilbert space that I'll call HAB, which is a tensor product of HA and HB. We can't really do that in quantum field theory, but we can do it in ordinary quantum mechanics. And I want to explain what in ordinary quantum mechanics would be the analog of this Riesz-Leiter property that we proved for quantum field theory. So, a general, okay. So first of all, in ordinary quantum mechanics, we do have two algebras. One which I'll call curly A acts on A, and curly B acts on B. Curly A consists of operators of the form A tensor the identity. A acts on A, and this is the identity on B. And curly B, I will often probably just write A tensor 1 rather than A tensor 1B. Curly B similarly consists of operators of the form 1A tensor little b, where little b acts on B, and 1A is the identity on A, so we might more informally write just 1 tensor B. So now, in quantum field theory, we proved that the vacuum was cyclic separating for each of our two algebras of regions U and V. In ordinary quantum mechanics, let's ask, what states are cyclic separating for either of the two algebras. So in other words, we'll ask what states in ordinary quantum mechanics would have the property that we prove for the vacuum in quantum field theory. Well, first of all, any state psi in HAB, which is HA tensor HB, well, any psi is the sum of Cij times some state I of system A tensored with some state J of system B. That would be a completely general state. But actually, the canonical form, you might want to ask, to what extent can we simplify this state by making a unitary transformation of the subsystem A or B? The canonical form up to unitary transformation of system of HB or HA is that psi is the sum of Ci times vectors I in state system A times I in B. The reason I said up to unitary transformation, we don't want to allow a completely general unitary transformation of the combined system. We're viewing the combined system as made of two subsystems, A and B. So we allow symmetries that preserve that property. So a unitary transformation of system B would preserve it, or a unitary transformation of system A. Not a combined unitary that scrambles the two subsystems. But the canonical form of what I'm telling you is that this matrix can be diagonalized by unitaries acting on just one side or the other, and actually not just diagonalized, but you can assume that the Ci are non-negative. And you can really assume they're positive. Well, okay. Now, let's ask, so does psi have the Rieschlieder property for the algebra curly A that acts on HA? Well, a general operator O in this algebra maps the state I to a sum over J of coefficients I should call this O, not A. Coefficients Aij times J. Right, this is the most general form of an operator that acts on system A. So then O acting on psi is the sum over J of Aij Cj times J of system A tensored I of system B. So you see that if the states I of system B are a basis, if and only if the states I are a basis of HB, well, it would be enough if they span HB. Sorry. Okay. When I put the sign this canonical form, I should have said that the IA and the IB are orthonormal. Every state can be put in this form with positive coefficient C and orthonormal vectors IA and IB. There might not be enough of the IAs and IBs to be bases, assuming you want the CIs to be all non-zero, but they will be orthonormal. So if the IA are a basis of HB, then you see that states of this form span HA tensor HB. Because the AIJs are completely arbitrary. So the J's are completely arbitrary states of the system A, so we can think of them as a basis. In writing this formula, we can assume the states JA are a basis of HA. So there's no restriction on the states JA, and we're picking O, so there's no restriction on the coefficients AIJ. So this state O psi is a completely general state, except that I runs over one of the states of B that appears in this decomposition of psi. So if the states of I sub B are a basis of B, then this is a completely general state. So the states O psi span HAB if and only if the states IB are a basis of B. They were orthonormal, so they're a basis if there are enough of them. Otherwise, they might span a proper subset rather than being a basis. So the Riesch-Leiter property is true if and only if, when we go to this canonical form, IB is a basis of HB. Any questions on that? Yes?
I'm confused with the notation you started with, where you put an I on both sides.
Okay, we can put a prime if you want. I thought if I called them I sub A and I sub B, I sub A was the ith chosen state of system A, and I sub B was the ith chosen state of system B. So they're different states. One lives in HA, one lives in HB. I thought it wouldn't be confusing to label them both as I because the subscripts would tell you which Hilbert space they're in. If you do find it confusing, put a prime everywhere on I sub B.
Sorry, I find it confusing because it seems as if they have the same dimension or something like that.
No, these are all I asserted here was that these are some states. I made the assertion that every state of the combined system, well, first of all, I think you didn't question this assertion.
Because I was hoping I and J running over different
They do.
over different dimensions.
They do, in general. So here, I and J run over different dimensions. Nevertheless, the canonical form has equal numbers. You see, different dimensions would mean that the original matrix Cij is a rectangular matrix. But if so, up to a change of basis, it has rows and columns of zeros. Rows or columns of zeros. The canonical form of such a rectangular matrix has some rows, columns of zeros, and some non-zero elements on the diagonal that are positive. That's the canonical form. So the canonical form of a rectangular matrix up to unitary transformations acting on the side that's bigger is what I assumed in writing the second formula. Any other questions? Not asking questions is supposed to be an acknowledgement that you understand and agree with the arguments. Okay. The canonical form of a general state is like this, but there might not be enough IAs or enough IBs to be bases. In general, they're just orthonormal. We learned that the state psi has the Riechlider property for the algebra A if the I sub b's are a basis of B. Now we can ask the opposite question. If O psi equals 0 and O is in A, does it follow O equals 0? Remember, the corollary of the Riechlider theorem was that if an operator in the algebra annihilates the vacuum, then the operator is 0. So we could call that the dual Riechlider property. Let's ask if the state psi has the dual Riechlider property. This should have been Ci here. So, you see, the operator O is anything at all in system A. So annihilating psi would imply that it annihilates all of the states I sub A. So in order for it to be true that a non-zero operator in the algebra, in order for it to be true that an operator, so the dual Riechlider would say, so if O annihilates a state like this, does it follow O is 0 on the whole Hilbert space HA? Well, O annihilating this state means that it annihilates all of the I sub A's. O annihilates this state if and only if it annihilates all the I sub A's, because the coefficient multiplying I sub A are the linearly independent states I sub B. So the question is, if O annihilates all the I sub A's, is O 0? Well, hopefully you know that that's true if and only if the I sub A's are a basis, or at least if they span the Hilbert space. But since they're orthonormal, the answer is yes, if and only if the I sub A are a basis. I'll call you in a second, but I could have avoided giving that argument as follows. I had proved that the Riechlider property holds for the algebra A if and only if the states IB are a basis of B. The same argument shows that the Riechlider property holds for the algebra B if and only if the states IA are a basis for A. But you know that the dual Riechlider property for A is the same as the Riechlider property for B. That was how we proved the dual Riechlider property in field theory. And the argument would have worked the same way for quantum mechanics. So the conclusion is that in ordinary quantum mechanics, a state well, first of all, the canonical form is that the CIs are all positive, because if they were 0, we could drop some terms from the sum, and the IAs and IBs are orthonormal. So any state can be put in this form. But so when I talk about a state of this form, it's really any state up to a change of basis. But such a state obeys the Riechlider property for both algebras A and B, or equivalently, it obeys Riechlider and dual Riechlider for A if and only if the states IA and IB are bases. So that's what Riesz-Leiter means translated into the language of ordinary quantum mechanics. Now, there was someone I promised to call on after momentarily. What was the question? Well, every state can be written in this form, and I can assume the CIs are all positive, because if some of them are 0, I just write a shorter sum without those terms. So by definition, in this formula, in this sum, I only include non-zero terms. I write the shortest such formula for psi. And when I write the shortest such formula for psi, then the argument shows, then CI by definition are all positive, and the states IA and IB are orthonormal. Every state has this property up to the right choice of basis in writing it, up to canonical. The canonical form of any state is like that. Then for such a state, we showed that the Riesz-Leiter and dual Riesz-Leiter properties are true if and only if the states IA and IB are both bases. Any other questions? So, of course, for this to be true, it has to be the case that the two Hilbert spaces have the same dimension. Because the number of vectors I sub A in the sum is the same as the number of vectors I sub B in the sum. And if the IAs are a basis of A and the I sub Bs are a basis of B, then the two Hilbert spaces have the same dimension. So, in this situation, this situation does not represent maximal entanglement between the two Hilbert spaces A and B. It represents what you could call full entanglement. It's not standard terminology, I have to warn you. So some people don't like it. But it's useful to have a term that represents this concept, and there is no standard term in the literature. But we could say that the state is fully entangled, meaning that the density, all eigenvalues of the density matrices are invertible. If we have such a state, the density matrix of system A, which is the trace over B of psi psi, is the sum of Ci squared times IA, IA. And similarly, rho B is the sum of Ci squared times IB, IB. And you see, since the states IA are a basis and the states IB are a basis and the CIs are all non-zero, rho A and rho B are invertible. So the Riesz-Leiter property in ordinary quantum mechanics is equivalent to saying that the density matrices are invertible. Their eigenvalues are all non-zero. Maximal entanglement would say that the density matrices are multiples of the identity. The CIs are all equal. Here we just have full entanglement. The density matrices are invertible and the CIs are all positive. So, in this sense, the two regions in quantum field theory are fully entangled, or they have the property that's analogous to full entanglement in ordinary quantum mechanics with invertible density matrices.
I have a sort of naive question, but if you're fixing always a psi at the beginning and then you're chasing a basis which is orthonormal with all these properties, so this basis would depend on the psi that you...
Yes.
And it would be changed.
Yes.
A global basis.
Yes. In ordinary quantum field theory, we started with the vacuum. I made an argument that's not true for all states. It's actually true for generic states. But I didn't prove that. Actually, at the beginning, I think at the beginning, or maybe I forgot to say it, everything I've told you is in my lecture notes. which I think I forgot to say this. Oh, sorry. We've gone on more than I realized. In here, which is my only paper with the word entanglement in the title, so if you forget the archive number, you can find it. You could find this proof and read over it more carefully. But, sorry, what was I saying concerning your question? Okay, sorry. In ordinary quantum field theory, we proved it for one state. It's actually true for a generic state, but we didn't prove that. And you can see that it also in quantum mechanics, first of all, in quantum mechanics, this property is impossible if the Hilbert spaces have different dimensions. If they have the same dimension, it's true if and only if the density matrices are invertible, which is true for a generic state. So in ordinary quantum mechanics, we've proved that when the property is possible, it's true for generic states, but the proof involved looking at the details of a particular state. Now, since this property is possible in ordinary quantum mechanics, you could ask, is something happening in quantum field theory that's impossible in ordinary quantum mechanics? Well, what I think is impossible in ordinary quantum mechanics is that in quantum field theory we could make the open set smaller and the property is still true. So an open set U has the Riesz-Leiter property, but a smaller open set U prime has the Riesz-Leiter property, and a still smaller open set U double prime, which I can't, well, it doesn't show up well the way I'm drawing it, but anyway, it's meant to be there. A still smaller open set still has the Riesz-Leiter property. No matter how little it is, it still has the Riesz-Leiter property. In quantum mechanics with finite dimensional Hilbert spaces, since the Riesz-Leiter property is only possible if they have the same dimension, if we make one of them smaller, we can't have the Riesz-Leiter property. However, you could go to ordinary quantum mechanics with infinite dimensional Hilbert spaces, as for example in atomic physics. And then I believe it is true that, for example, if you consider a quantum mechanical system of 7 bodies, and you consider as subsystems the 3-body and 4-body states, I believe it's true that a generic state will have the Riesz-Leiter property. The Hilbert spaces are of infinite dimension, so there's no notion of one being bigger than the other. And if you instead consider decomposing the ordinary matter system into 2 particles and 5, I think the 2 and 5 will have the Riesz-Leiter property for a generic state. So that actually will be an example in ordinary quantum mechanics where you can make the Hilbert space smaller, and the smaller one still has the Riesz-Leiter property. What I think is extremely hard to achieve except in quantum field theory is that you can continuously make the open set smaller. And at each step of the way you have the Riesz-Leiter property. I wasn't successful in seeing how to do that in ordinary quantum mechanics, but I also don't have a proof. So I invite any of you here to offer either a proof or a counter argument. Any other questions? Well, I have approximately minus 2 minutes, I think. Is that correct? Is that right? Can I pretend it's plus 2? Okay. So, well, I won't start my second topic. We finished the first topic I announced this morning, and given the time it took for one topic, my guess is the second topic will also take the same length of time tomorrow, so we won't do much more. But I did want to spend the remaining 2 minutes to tell you a fun corollary of this, which is that, well, I'll state it a little bit informally. If you take the energy integrated over all of space, it's non-negative, of course. But suppose you take the energy density and integrate it only over a partial region in an initial value surface. For example, you integrate it only over the region where the absolute value of the spatial coordinates is less than 1. I want to prove to you that h sub d can't possibly be non-negative. So, first, H sub E doesn't annihilate the vacuum. Why is that true? Well, the dual Riechlider property tells us that. H sub D is an operator that lives in a small open set, namely the open set where x is less than 2, let's say. So it can't annihilate the vacuum. So pick chi such that HD on omega, matrix element with chi, is non-zero. And in the 2D space spanned by omega and chi, it is true, though, that the vacuum expectation value of HD is 0. Because the vacuum expectation value of the energy momentum tensor is 0. And HD was obtained by integrating the energy momentum tensor over a small open set. So in the 2D space spanned by, let's say, with this basis omega and chi, Hg is represented by a two-dimensional matrix. And the upper left element is 0, and the off-diagonal elements are non-zero. Well, you see, alpha, or maybe alpha bar, is this thing, which is non-zero by the choice of chi, and the upper left element is 0 by this property. We don't know what's the lower right element. I'll just call it M. But such a 2 by 2 matrix can't be non-negative. A 2 by 2 matrix like that can't be bounded below by 0. It always has a negative eigenvalue. So therefore, HD is not equal to or greater than 0. I thought that was a fun corollary of the dual Riechlider property, so I wanted to explain it. Thank you.
So it's time for one question.
Presumably you can argue that it's also arbitrarily negative, right?
You can certainly argue that the expectation value of t00 is arbitrarily negative. When you smear it over a region of space, I don't immediately remember such an argument. Perhaps you know one, though. Okay. For the expectation value of t00 in a conformal field theory, once you know it's not bounded below by 0, it can't have any lower bound by scaling. And any theory for any theory that's conformally in very net short distances, the same applies. There probably are more things I'm forgetting right now. Yes?
Is there a way that the Riechlider theorem generalizes to Kerr backgrounds?
Yes. Unfortunately, the Riechlider theorem is true in any real one true statement is that the Riechlider theorem is true in any real analytic spacetime for any real analytic state. See, it's not the Riechlider property, even in Minkowski space, isn't true in all states. It's true in sufficiently nice states. So I'll have to, in a given space-time, it'll be true for a sufficiently nice state, which I have to describe. Any state with a Euclidean preparation is sufficiently nice in a real analytic space-time. There's a literature on that going back 20 years or so, but one version of the proof is in a recent paper I wrote with Alex Strohmeyer, which is mainly on the time-like tube theorem, but it includes a proof of this. Unfortunately, to prove that kind of thing, I would have had to have been giving more than 2 lectures on general background of algebraic QFT. Assuming that my third lecture is supposed to be closer to applications to gravity, I won't be able to explain that.